So let me share the screen. So can you see my screen?
Yes, we can.
You can see it. So I will send you the course outline, but the first topic will be vector spaces. So vector spaces are really important. There are very many applications, and as we go along, we might encounter some of them. They are very useful in almost every area. You go to economics, you go to technology, engineering, anywhere you go, even in medicine, there are things that physics and so on. You'll be able to find some use for this. Anywhere there is data, you will find use for vector spaces, because mostly data can be expressed that way as a vector or as many vectors. Now we will start with the definition of a vector space. So this one says that let V, if V is an empty set, and U and V are elements of V. Note that we will be using a bar on top of the elements. I forgot to put one on U, but it should be bar U and bar V. So bar U and bar V are elements of V, and alpha is a real number. We define two operations on V as follows. So we must, elements of V are U and V, then we define some operations on elements of V as follows. We define vector addition, and we also define scalar multiplication. So the vector addition is defined in such a way that if you add two vectors, again, I forgot to put the bars on top of the U and V, but those should be vectors. So bar U and bar V, when you add them, you should get another vector or another element of V. Also, if you pick any vector and multiply it by a scalar, you should also get another element in V. So there are these two operations. We have vector addition and scalar multiplication. For now, we don't have any multiplication of vectors. You don't multiply two vectors. You can only add two vectors, but you can multiply a vector by a scalar. So once you define these two operations, we will say that V is a vector space over R if the following properties hold. So we'll go through the properties one by one. The first property is that if you add two vectors, you should get another vector in V. If two vectors, again, I forgot to put the bar. I need to be a little more careful here. There should be bars on U, another bar on top of V, and another bar on top of W. Alpha and beta are numbers, they are not vectors, so there's no need for a bar on top. Also, the next property says that addition of vectors is associative. So I can put the brackets either on V and W or on U and V, and the answer will still be the same. So vector addition is associative. And the third property says there's a special vector which we denote by bar 0 in V, such that if you add this vector to any other vector, you don't change the vector. So bar U plus bar 0 will still be equal to bar U. Now this is always true, and this vector bar 0 is called the zero vector. So the zero vector is unique. A vector space cannot have more than one zero vector. There's only one zero vector in the vector space. Then for all the fourth property says that if you pick any element, any vector in V, again, I forgot to put the bar up here. This means that we can find another element which we choose to denote by minus V, such that if we add this element to the vector V, we get the zero vector. So this should be the zero vector. It should be zero with a bar also. Keep forgetting. So we should have a bar up here. But maybe I could try to correct the notes again before I share. And replace the one I've shared, because the one I've shared is already on Somas. If you go to Somas, you should be able to download the file. There's a link to the download. The fifth property says that if you, the order in which you add the two vectors does not matter, so that bar u plus bar v will be exactly the same as bar v plus bar u. And here we say that vector addition is commutative. So that's the commutative property of vector addition.
Excuse me, sir.
Yes.
There's people waiting to be let into the class.
They need to learn to join early.
Okay, sir. But the link is not the same that we used last time.
It's not the same.
Yes, they were waiting on the other one.
Okay, then maybe the mistake is mine. I will correct that.
Okay, thank you.
Okay, that's why it is asking you to asking for admission.
Yes.
Very strange. I thought I used exact same link last time. We can give them a few minutes to join, like 1 more minute. But the video will be shared. I will record whatever they have missed. I will share it, and they'll be able to record. They'll be able to watch it again. So I think they are all in now. So we can proceed with our properties. We have already seen the first 5 properties. The first 5 properties are all talking about addition. So the next set of properties will now connect the scalar multiplication and addition. Remember, the first, we had 2 operations. One of them was addition of vectors, which is here, and scalar multiplication. So the first 5 properties are focusing on just the addition. Now we want to connect the addition to scalar multiplication, the remaining properties. So this again is just from the definition of a scalar multiplication. If you multiply any vector in V by a scalar or a number, a scalar here means a real number, then you still get a vector in V. So I'll try to send the correct link. I don't know why there's confusion on the link. I thought I used the same link last time. At least my calendar shows the same link, but I will correct it so that everyone has an email showing the latest link. So the properties, we have seen that if you multiply any vector, this is bar V multiplied by alpha, you will get another vector in V. It will still be an element of V. Now, the next property shows that the scalar multiplication is distributive over vector addition. That's property number 7. So that if you multiply the sum of two vectors by alpha, then it's the same as multiplying each vector by alpha and adding them. So that's the 7th property. The 8th property here says you can, if you have two scalars, alpha and beta are numbers, you multiply them first, then you multiply by a vector. It's the same as putting the brackets. You can multiply the vector by beta first and then multiply by alpha. It will still work. Give you the same answer. So if you multiply the sum of two scalars, so alpha and beta are scalars, they are numbers. If you multiply this sum of two scalars by a vector, or rather, if you multiply a vector by the sum of two scalars, alpha plus beta u, you'll get the same thing if you did alpha u plus beta by u. So that's the same. And if you multiply any vector by 1, you should still get the same vector. So 1 by u will be equal to by u. So if anytime you're given a set, these two operations will have to be defined, the vector addition and the scalar multiplication. Then you have to go through all these, I think there are 10 properties, and check that the 10 properties are true before you can conclude that that set is a vector space. Now, since we are picking all the scalars alpha from the real numbers, we will say that then it is a vector space over the real numbers R. And the elements of V are called vectors. So any element in a vector space will be called vectors. So there are many types of vector spaces. We shall start with what is closer and familiar, and later on we shall look at other types of vector spaces. So a simple example is the set of real numbers. Here you just define the numbers now become your vectors, and addition is just a normal addition of real numbers, and multiplication is also the normal multiplication of real numbers. And under these properties, under these conditions, you will see that all the 10 properties will be satisfied. I will not go through these 10 properties for this example, but in the next example we shall do that. The next example says we consider the set of all ordered pairs of real numbers. This is just the Cartesian plane, the XY plane. So all the points in that plane, you consider them, and they can be represented as ordered pairs where we have XY and XY. Both X and Y are real numbers. You're familiar with this notation for sets?
Yes.
Okay, so that's good. So we define vector addition as follows in this set. So if U1 is X1, Y1, and by U2 is X2, Y2, and by U1 plus by U2 should be equal to you add the elements that are in the first coordinate for both vectors, and then the second component for the sum will be you add the elements that are in the second slot for both vectors. So clearly, when you add these two, you will get another vector in R2. So our addition is well defined. If you pick a vector in R2 and you multiply it by a number or a scalar, you still get another vector in R2. So we now have vector addition and scalar multiplication properly defined, and we need to check that all the other properties are satisfied. So we'll verify that R2, the set of all ordered pairs of real numbers, is a vector space over R. So R, it's also possible to have vector spaces over other fields But for now, we shall focus on vector spaces over the real numbers. So let's verify that the R2 is a vector space. Already this was checked. If you add any two vectors in R2, you will get another vector in R2. This should be bar U1 and bar U2. Okay. Then the second property is just to check that addition of vectors is associative. So we have three vectors, U1, U2, and U3. We start by putting the brackets around U2 plus U3. And this is what we get. When we add U2 to U3, this is what we get. But from the definition of addition, we can now write this as x1 plus x2 plus x3 in brackets, and y1 plus y2 plus y3 in brackets. So that's the next step. But what we are adding in here are just real numbers, right? So we can use the properties of real numbers in here, because we know that addition of real numbers is associative. So I can move this bracket from x2 and x3, I can move them to x1 and x2. I do the same for the next slot. And then again, I use the property of addition for vectors. I can split this into two vectors, x1 plus x2, y1 plus y2 as one vector, plus another vector, x3, y3. But this first is simply the sum of u1 and u2. So we can put that in brackets and then add that to u3. So we have shown that the addition of vectors in R2 is associative. So that's what we have shown. If you add any two vectors, you can put the brackets in the last, if you add any three vectors, you can put your brackets anywhere, either on the first two or the last two, and it will still work. So this proves that the addition on this addition is associative. So now the next property is we need to find an element in the set R2 which behaves like 0. In other words, an element which when added to any other vector does not change the vector. So if we set bar 0 to be this vector where both the first and second component are 0, then for all vectors in R2, if we can do this, u1 plus 0 will still give us u1. This is u1. I think I'll have to do some corrections and scan again. It's not much easier if they were tight to correct, but I'll do the correction and scan this. But this should be u1. So u1 plus 0 is not changed. It's still u1. So this should be, and the bar should be up. The notation we shall stick to is where the bar is up. This is a mistake again I made. I will try to limit these mistakes in the next set of notes. So we also check that vector addition is commutative. In our list, I think this is a fifth property, but I went to it before I did the fourth property. So we shall just change the order here. So by u1 plus by u2 can be written as this, x1 plus x2 as the first component, and y1 plus y2 as the second component. But again, remember here, we are just adding real numbers, and addition of real numbers is commutative. So x1 plus x2 can be written as x2 plus x1, and y1 plus y2 can also be written as y2 plus y1. And then we split this again back into two vectors. We end up with u2 plus u1. It should be only one plus, not two plus signs. So we end up with u2 plus u1. So we have shown that u1 plus u2 is the same as u2 plus u1, and therefore vector addition is commutative. The next one was what was supposed to be the fourth property. If we pick any vector u, we have x1, y1, then the vector minus u1, which we define as just the negatives of the elements in the component of u1, we see that if we add u1 plus this minus u1, we get the 0 vector. Did I leave this property out? So this vector here is called the negative of u1. And if you add that vector to u1, you get the 0 vector. So every vector in R2 will have a negative. Then the sixth property now connects the scalar multiplication to the vectors. This one is if you multiply any vector in R2 by a number alpha, you still get another vector in R2. So the next one again simply checks that if you multiply the sum of two vectors by a number, so this is alpha is a number, then u1 is a vector, and u2 is another vector. So alpha by u1 plus by u2, it should be a bar here, turns out to be equal to alpha by u1 plus alpha by u2. You can follow these computations and you will see how we end up with this. So this tells us that this scalar multiplication is distributive over vector addition. So we can check the next property. If we add two numbers, alpha and beta, and then multiply by a vector, we end up with, again, alpha multiplied by the same vector plus beta multiplied by the same vector. So this property holds for R2. And the ninth property is if you multiply alpha and beta, u1 and alpha beta, you can actually put your brackets anywhere. You can either put the brackets between for immediately after alpha and immediately before beta and immediately after u1, or you can put them. You can put the scalars in brackets and leave out the vector. The answer will still be the same. So if you have this kind of situation where you have two scalars being multiplied by u1, you can always start by multiplying using the first scalar and followed by the second scalar. And this process here will show you how that works. I think so the movement from this step to this step is simply making use of the property that real numbers are associative. So you can put the brackets on alpha or beta, or you can put the brackets on beta and x1. This is because multiplication of real numbers is associative. And what is happening inside the brackets is just operations on real numbers. So you can use the properties of real numbers. So the seventh, the last property, the 10th property, if you multiply any vector in R2 by 1, then you will get the same vector, u1, and that is illustrated again here. And therefore, R2 is a vector space over R. We say it's a vector space over R because all the scalars are real numbers. The scalars were, say, from the complex numbers, we would say it's a vector space over complex numbers. So the next example we'll give of a vector space is a set of ordered triples of real numbers. And this set is usually denoted by R, this fancy looking R raised to 3. You are probably familiar with this symbol. Have you met this symbol in SMA 101 for the set of real numbers?
Yes.
Good. So we make the claim that this set is a vector space over R. We shall not prove it, but all we shall do in this case is define the addition of vectors in R3 and the scalar multiplication in R3 as well. So addition of vectors is just the usual. You add the corresponding components in each vector. But U1 plus U2 will be X1 plus X2, Y1 plus Y2, and Z1 plus Z2. And if you multiply the vector by a scalar, it simply means you multiply every element in the vector by the same scalar. So that alpha U1 will be alpha X1, alpha Y1, alpha Z1. So those are the two operations you need. Now with these two operations, you can show that R3 is a vector space over R. All the 10 properties that we listed will be satisfied by R3 using these two operations, the vector addition as defined and the scalar multiplication as it has been defined. So a lot of these may be new to you. So you really need to go back and sit down and read through this work very carefully, be able to follow it. And you'll have to read it as soon as possible. Don't wait too long to read it, because then you will have forgotten. If you are not able to remember, you will find the video. I will share the video as well. So the next thing we note is that if we consider vectors in R2, is there someone making a comment or someone trying to join? So vectors in R2 can be represented in the Cartesian plane. So like this vector 2, 1, simply represented by the vector whose terminal point is at the point whose coordinates are 2 and 1, where x is 2 and y is 1. And you could also do the same in 3 dimensions. In 3 dimensions, you need 3 coordinates, so you need 3 axes. X, it should be the y-axis and the z-axis. So we want to show the point 2, 2, 1, where the x coordinate is 2, the y coordinate is 2, and the z coordinate is 2. So to do this, we'll have to create a small cuboid. It's a cube or a cuboid. Can't be a cube because they're not the same length. So now, our cube has the same length across. Every side has the same length, or the sides are just squares. So this the vector we are looking for is the one that is at this corner, the one that is closer to us, or appears to be closer to us, this one here. So that's the point we are looking for. That's the point 2, 2, 1. You obtain it by moving 2 units in the positive direction of x, 2 units in the positive direction of y, and 1 unit in the positive direction of z, and then create this cuboid like that. And then the point of the cuboid up here will be the terminal point of the vector 2, 2, 1. So the same ideas we have done for R2 and R3 can be extended for a general case. So instead of 2 or 3, you have Rn. So Rn is basically the set of all n tuples. N tuples is the term you'd use instead of ordered pair or ordered triple. When there are more than 3, you call them n tuples. So it will be made up of a list of these n numbers. So they will look like vectors, but they will have n numbers inside the brackets. So instead of 2 or 3, you can have 4, 5, or even more. And we require that each entry is a real number because we want a vector space. We can work with that. It's Rn anyway. So each entry must be a real number. So we define addition in Rn as follows. It's similar to what we did in R2 and R3. Just add the corresponding components. So this would be x1 plus y1, x2 plus y2, xn plus yn, all the way. So the other thing that we define again is scalar multiplication. So if you multiply any vector by a number, then it's the same as multiplying each entry in the vector by the same number. So this gives you the scalar multiplication. So under these two operations, Rn will be a vector space over the real numbers. We shall not go try to prove it. So here it gives an example when n is equal to 4. So elements in R4 will look like this. They will just have 4 components. When you add them, this is what you get. And when you multiply them, it's simply the same as multiplying each component in the vector by the same number. So I'm just stating again the same what we stated earlier, that if we define the two operations earlier seen of vector addition and vector scalar multiplication, so vector addition and scalar multiplication if defined as above, then Rn turns out to be a vector space over the real numbers. In other words, all the 10 properties will be satisfied. Now, the only challenge we have when we are dealing with values of n that are bigger than or equal to 4, it will be difficult to display the vectors graphically, but we can develop techniques that are enable us to handle them algebraically. So this course is supposed to help us build those techniques that allow us to handle vectors that are bigger than the vectors in R2 and R3. They have more components. So even without drawing them, we can come up with properties that allow us to describe a lot of objects in R2 or Rn. And also there are many situations in life where you need more than n coordinates, more than 3 coordinates. So it is useful to learn them because they can really be applied in many places. We will try to look at some applications towards the end of the semester. For now, the aim is to get you to learn the basics, the basic science behind it. So I had also mentioned earlier that Rn is not the only type of vector space. There are others, but we will discuss them later in the class. So for the time being, we focus on Rn and some properties of vector spaces over R. So here's the first property. It's listed as a theorem. There is let V be a vector space over R, and let bar V be an element of V. So bar V is a vector of V, and lambda is a real number. So this theorem says that you multiply any vector by 0, 0 the number. You have to differentiate between 0 the number and 0 the vector. 0 the vector has a bar on top, and 0 the number has no bar on top. And the second one says if you multiply any scalar from any scalar by the 0 vector, you still get a 0 vector. So all these properties are properties that you need to keep in mind. We shall be using them later. So the proof for these properties follows. We'll not work on the proofs. You can look at them later in your own time and try to study them. Or maybe you can look at the first one. The first one says 0 V is equal to, we can replace the number 0 by the sum of the two numbers 0 and 0, and use a property that if you add two numbers and you multiply by the vector, then they should be equal to 0 multiplied by the vector and 0 multiplied by the same vector. And that means we have a situation where 0v is a sum of itself plus another vector. So one of them must be 0. And that forces 0 by v to be equal to 0. The second one follows similar lines. We have lambda multiplied by bar 0, where bar 0 is a 0 vector. Lambda multiplied by the sum of two 0 vectors. And we can see that this still leaves us with the option, with no other choice than the fact that if you multiply the 0 vector by any scalar, it doesn't matter what the scalar is. The scalar doesn't have to be 0. You will get the 0 vector. So this should be the 0 vector, not the number. This one here should be the 0 vector. Are there any questions up to that point? So you have an exercise here. For the next 5 minutes, you can solve this problem. Then you will share your answers. We resume in 5 minutes. So take the next 5 minutes to do the following exercise. You can see the problems from your side?
Yes.
Yes.
Yeah, so this is what is this is the task at hand now. Solve these ones. So have you completed?
Yes.
So what's the answer to the first one?
The first one is alpha 1, alpha 2.
Where are you getting alpha 1? What do you mean by alpha 1? You mean alpha multiplied by 1?
Yes.
So alpha multiplied by 1 is just alpha.
Oh, yes. Oh, alpha and yes.
Alpha and 2 alpha.
Yes, and 2 alpha, sorry.
Okay, that's correct.
Yes. Then the
What?
second.
Mm.
The second is 525.
525.
Yes.
525.
No, the vector, the vector. The vector.
So the first component is what?
Yes.
The first component is what?
The
5.
first component is 5.
Oh, this one. 2 by u plus 3v.
Yes, 2 by u
First
plus
component is
3 by
5.
v.
And the
Yes,
second component?
25.
Good. So 5 as the first component and 25 as the second component.
Yes.
Does anyone else have a different answer? You're all in agreement. What about the third one?
The third one is the first component is 1.
Yes.
Then the next component is -3.
Yes.
And the third component is 1.
Okay, that's fine. What about the fourth one?
The fourth one, the first component is 2.
Mm-hmm.
The second component is 6.
Mm-hmm.
And the third component is 14.
Okay, I think that's fine. I don't think anyone else has a different answer. So now we make another definition. We are going to define what we call the subspaces. So let V be, we say let V be a vector space over R, and let W be an empty subset of V. Then W is said to be a subspace of V if W itself is also a vector space. Okay, so you can find a smaller subset of the vector space which also behaves like a vector space with the same addition and scalar multiplication. Then this smaller set is said to be a subspace. So we need to get the difference between a subset and a subspace. Not all subsets will be subspaces. The only subsets of V that can be subspaces are the ones that also behave like a vector space, and not all subsets will behave like a vector space. So it's important to determine, given a subset of a vector space, we need to have some way of determining whether that subset is a subspace, right? So one way of doing that is to pick the subset on its own and run through all the 10 properties and confirm that those properties are satisfied by the subset. And if they are, we can conclude that the subset is a subspace of V. But that would be a tedious process. So we are going to use the following theorem, which provides us with a shortcut. So we shall not prove the theorem, but we shall use it. So the theorem says the following. Let U be a non-empty subset of a vector space V. So then U will be a subspace of V if the following happens. The first property is that U should contain the zero vector. That is one. And then if we pick any two vectors in U, when we add them, we should get another vector in U. So we stay within U. Any vectors we pick from U, when added, will give you another vector inside U. That's what the second statement says. So the last property that is required is that if you multiply any vector in U by a scalar, you will also get a vector in U. So instead of checking, if you are looking at a subset of V, assuming you already know that V is a vector space, once you know that V is a vector space and you are looking at a subset, you can check that that subset is a subspace by confirming that the three properties, only these three properties are satisfied. So that is enough to show you that a subset, a given subset, is a subspace. Now, if even just one of these properties is not satisfied, then the subset fails to be a subspace. So if you want to prove that a subset is not a subspace, you just need to confirm that one of these properties is not satisfied. That's all you need to do. You don't need to check all of them to disprove, but to prove, you must check all the three. To prove that it is not a subspace, you just need to check that one of them is not satisfied. So we'll look at some examples. So we create the following subset of R2, which is made up of ordered pairs x, y, such that y will be equal to 2x. So our task here is to show that T is a subspace of R2. So we shall just follow the strategy. We check that all the three properties are satisfied. And we'll also make the observation that T contains vectors of the form x and 2x. This is because the y coordinate will just be, this description here tells us that the y coordinate will always be twice the x coordinate. So we can write the vectors as x, 2x. Any vector in T will take this form. So let's check. Is the zero vector in T? We need to check if the zero vector in R2, the zero vector is this vector with zeros in all the slots. This vector is definitely in R2 because if you check if it satisfies this equation, it does, because x 0 is equal to 2 times 0. So this equation is satisfied, and therefore the zero vector is in the set T. So let's pick any two vectors in T. Remember, we said that vectors in T will be of the form where the y coordinate is twice the x coordinate or the x component. So x component is x1, and y component rather would be 2x1. And then u2 will be equal to x2, 2x2. So these are two vectors, possibly different vectors in T. So when we add them, we need to show if we will still get another vector in T. So we proceed and add them. We have u1 plus u2 will be equal to x1, 2x1 plus x2, 2x2. Yeah. And when we complete the addition, we have, it still ends up as x1 plus x2 as the first component, and 2 multiplied by x1 plus x2 in brackets. So clearly you can see that the second coordinate, the y, or rather the y component here, or the second component of the vector, is 2 times the first component. And that is all we need to confirm that a vector is in T. So this vector is definitely in T, and that proves that if we add any two vectors in T, we still get another vector in T. So the last property is that if you pick any scalar and multiply it by a vector in T, we need to show that we will also get another vector in T. So we proceed to do that exactly with the vector u1. We multiply it by alpha to get alpha x1 in the first component and alpha 2 x1 in the second component. This can all be rearranged as alpha x1, and then the second component is 2 multiplied by alpha x, x1. So again, clearly here you can see that the vector that we have at the end, the second component is twice the first component. And that is what vectors in T look like. So it means that this vector is definitely in T. And that means if you multiply any vector in T by a scalar, you will get another vector in T. So now what do we do now? All the three properties are satisfied. We have no choice but to declare that this set T is a subspace. So T is a subspace because all the three properties are satisfied. So the next example, we are given a subset. Now what you'll notice about this, let's go back one step. Huh? This set T is basically the straight line y is equal to 2x, which runs through the origin. So it's definitely a subset of R2. It is not the whole of R2. It's a proper subset of R2 because it just consists of all the points in R2 which lie on the line y is equal to 2x, and they pass through the origin. And since it passes through the origin, that's why the zero vector is guaranteed to be in the set. So the next example says, let T be equal to this set made up of ordered pairs which lie on this line y is equal to x plus 1. So our task is to determine if T is a subspace of R2. So we check some properties. We check the first one, and we can clearly see that the zero vector is not in T because 0 is not equal to 0 plus 1. Any vector in T must satisfy this property, and therefore the zero vector is not in T. That alone is sufficient to conclude that T is not a subspace. So with that alone, you don't need to go any further. You can easily stop there and claim that T is not a subspace. So, but I've checked all the other three properties just to show you how it works. And we see that even the other two properties remaining are not satisfied. So we check the second property. If you pick any two vectors in T, so this set T, it means the y component will always be of a form the x plus 1. So if the first component is x, the second component will be x plus 1. So that's what we are doing at the next step. We pick two vectors in T, and both of them will take this form: x1, x1 plus 1, and x2, x2 plus 1. So again, if we add them, I forgot the bars again here. This should be bar u1 plus bar u2. Bar u1 plus bar u2 will be equal to x1 plus x2. And when you arrange all this, you will have x1 plus x2 in brackets. I'll skip some steps and just go into the last part. So you'll have the first component is x1 plus x2. The second one is x1 plus x2 plus 2. Now, this does not satisfy the requirement for elements in T. That's the second component to be the first component plus 1. In this case, after adding them, the second component is the first component plus 2. And that does not satisfy the requirement for elements of T. So we see that when we add two vectors in T, we don't get another vector in T. The same applies to the third property. If you multiply a vector in T by a scalar, you don't end up with a vector in T. Because here you can see clearly that the property where the second component should be equal to the first component plus 1 is not satisfied. And therefore, this vector cannot be in T. So this is an interesting example where all the three properties are not satisfied. And so the thing is, if you have this kind of situation, So for this kind of situation, if you want to prove that something is not a subspace, you just need to confirm that only one property is not satisfied. Once that is confirmed, you're done. You don't need to bother with the others. So you can pick which one you find easier to check, and that is the one you use to check that a set is not a subspace. So the conclusion here is that T is not a subspace of R2. So the remark follows here. So it says if any of the conditions fail, we do not need to check the other two. So we can take a 5-minute break, or you are not tired?
We are not
Yes, we are
tired.
not.
Muko chonjo bado?
Yeah.
Hey, ulikula breakfast mzito? Okay, that is good. So here's another example. We consider the set U, which consists of vectors in R2 of the form x0. So we don't care what is in the first component, but the second one must be 0. So we want to prove that U is a subspace of R2. Oh, I've made a mistake here. The first property should be 0, 0 is an element of U. So this slanted line should not be there. This should be 0, 0 is an element of U. That is clear because 0, 0 satisfies the property that the second entry is 0. So it definitely belongs to U. Now, if you pick any two vectors in U, let's call them by U1 and by U2. If we add them, we still get another vector, which is in U. Because what happens is, again, the only requirement is that the second component must be 0. And that still holds after we add the vectors. The result of the sum of the two vectors still gives us another vector in U. So the second property is satisfied. The third property also, we check if the scalar multiple of the vector U1 will also be in U. And when we do that, we have alpha multiplied by x1, 0. And this simply simplifies to alpha x1, 0 as a component of our vector. Again, this automatically satisfies the requirement for vectors to be in U. In other words, the second component must be 0. We don't worry about what is in the first component, but the second one must be 0. So the first one can be any real number, as stated in the example. So all the three properties are satisfied. So our conclusion here is that U is a subspace of R2. So maybe you may want to look at what is common to the two examples where the subset was a subspace. Here you will notice that this is simply if you are in the Cartesian plane, this is simply the x-axis, because the y-coordinate on the x-axis is always 0. So this subset of R2 is just the whole of the x-axis, and it passes through the origin. If you consider the previous example that we did earlier, the first example to check if again, this one, y is equal to 2x, is a line that goes through the origin. But if you look at the example which was not a subspace, you have a line y is equal to x plus 1. Yeah. So this one, you can see clearly this line does not pass through the origin. And all points on that line are the ones that form the set T, and we showed that this is not a subspace of R2. Therefore, in general, it can be shown that if the line does not pass through the origin, then the set of points on that line cannot form a subspace of R2. Let's try to admit some people. So so the conclusion there is that if you are in R2, any subspace will be a line that passes through the origin. That can be proved, but we haven't proved it here. But keep that in mind. So the other example that is simple to figure out is that every vector space is considered to be a subspace of itself. That is because every set is its own subset. So if you consider this vector space as its own subset, then you can think of it also as a subspace of itself. Then the set containing only the zero vector is also a subspace of every vector space. And it's normally called the zero subspace, or it can be called the trivial subspace. So this set consisting of only the zero vector is also considered to be a subspace. It doesn't matter which vector space you are in, this will always be true. These two properties will always be true. Let's look at another example. Now we consider a subset of R3, and we need to check that this subset is a subspace of R3. So we consider the subset which consists of all ordered triples x, y, z, such that x plus y is equal to z. So it means we can write vectors in W as follows. We can represent them as follows. The z or the third component will be equal to the sum of the first two. So if my first two components are x and y, third one, which is now supposed to be z, will be the sum of x and y. So any vector in W can be written as x, y, and then the third component must be the sum of the first two. So we need to check if this is a subspace of R3, because definitely these are vectors in R3. So let's check if it's a subspace of the vector space R3. So clearly the zero vector is in W because it satisfies the property that the third component is the sum of the first two. So the zero vector is definitely in the set W. Now, if you pick any two vectors in W, so we have by U1 and by U2 in W. If we add them, then we end up with x1 plus y1, x2 plus y2, and after some rearrangement, you have x1 plus x2 and y1 plus y2. So if you look carefully, the third component here is actually the sum of the first two. So our vector is in W. If you pick any two vectors in W, we still end up with another vector in W. Why have I changed this to U? Again, another mistake. So this should be W, not U. I will change this and rescan. So this should be W. What you can also do is note down, because the current set of notes I've shared on SOMAS, there's a link there where you can download these notes. They will contain these mistakes. So what you can do is, in your book, you note down that this is on which page? On page 18, this U should be replaced by W. Both, there are two U's here. This U and that U should be replaced by W. And also the last one here. This one should also be replaced by W. So it's a good idea to note this down, that on page 18 of the notes, you should make those changes. So I will assume that it's W and talk as such. So we have added U1 plus U2, and we have gotten a vector in W. We do the same for multiplication. If you multiply a vector in W, we end up with alpha x1, alpha x2, and then when we multiply the last one by alpha, we simply have alpha x1 plus alpha x2. So clearly you can see again that the third component here is equal to the sum of the first two. Okay, Dongi. Umesikia?
Kama ano.
Okay. Wewe mwe?
Itivamwe.
Oh, okay. I thought there were no people from Ukambani. No one was answering. What about Mwaigwa? Oh, there are no representatives. And anyone from Rift Valley? Kagasi? Not yet. So the third property also holds, and therefore you can conclude that W, remember this U is supposed to be W, hence you can conclude that W is indeed a subspace of R3. The reason it has to be W is because we call the set W. The set was W up here. So I'm not sure why I changed it to U again. So this confirms that U is a subspace of W. So another example here, which shows us how once you have two vector space subspaces, you can also construct a third subspace by just getting the intersection of the two subspaces. So it says if W1 and W2 are subspaces of a vector space V, then the intersection of the two subspaces will also be a subspace. So we'll prove this. So the proof, so now, okay, let's go through this. There's I may need to end the class earlier than 2 o'clock because of some clash, but hopefully by next week it will be resolved. So we need to check first if the subset we want to check if it's actually a subspace of V is the intersection of W1 and W2. So we need to show that first the zero vector is in the intersection. But we have some information ready. We already know that W1 is a subspace and W2 is a subspace. So both of them must contain the zero vector. And if both of them contain the zero vector, then it means the intersection of the two subspaces will also contain the zero vector. And therefore, the zero vector must be in the intersection of W1 and W2. I'm assuming you have learned this intersection of sets in basic mathematics.
Yes.
So this is not new. If you don't remember, it may be a good idea to review some of your knowledge of set theory. It will come in handy. So the next thing is to show that if you pick any two vectors in the intersection, then their sum will also be in the intersection. So let's pick the two vectors, U1 and U2 in the from the intersection. Then both of them must also be in W1, because if anything is in the intersection of W1 and W2, it must be in both W1 and W2. So both these vectors must be in W1, and also both of them must be in W2. Otherwise, they will not be in the intersection. And remember, W1 and W2 are subspaces. So if you have two vectors in W1, then the sum of the two vectors will automatically be also in W1, because W1 is a subspace, and the sum of the two vectors in W2 must also be in W2, because W2 is a subspace. So we have shown that U1 plus U2 belongs to both belongs to both W1 and W2, and therefore it must be in the intersection. So U1 plus U2 must be in the intersection of W1 and W2. The next property is that if U1 is in the intersection, then a scalar multiple should be in the intersection. That's what we need to show. So if it's in the intersection, again, we recall that it must be in both W1 and also W2. And since W1 is a subspace, if I multiply any vector in W1 by a scalar, I will get another vector in W1, so that alpha U1 is a vector in W1. The same thing happens with the W2. Alpha U1 will also be a vector in W2 because W2 is a subspace, and a scalar multiple of any vector in W will also be another vector in W2. And that is likely because W1 and W2 are both subspaces. And therefore, we have shown that the scalar multiple is in both W1 and W2, and therefore must be in the intersection of W1 and W2. This confirms that the intersection of two vector subspaces will also be a subspace. So anytime you have two subspaces, if you get the intersection will also be a subspace. We shall look at this later on again. We will need it. So do you still need a 5-minute break, or we can continue?
5 minutes break.
Yes, please, kindly.
Okay, so 5 minutes, then we continue. We'll be back at 12:36 according to my clock. So check your clock and make sure you only do 5 minutes. So we are back again. I think we can continue. So we now look at another topic. We call them linear combinations. So anytime we have a finite set of vectors from a vector space, we can construct some new vectors by getting multiples of the vectors and adding them. So we look at some examples. So let's consider some two vectors in R2. So we take the first vector to be 1, 0, and the second vector to be 0, 1. So we can create another vector by simply getting a multiple of u1. In this we get 2u1, and we also get a multiple of u2, that is 3u2, and then we add them. We get a new vector, 3, 2. So here we say that this new vector, 3, 2, is a linear combination of the vectors u1 and u2. So by changing these multiples, we keep getting new vectors. So I can change the multiples, say I can, instead of 2, I can have 1 here, and instead of 3, I can have -4. I will still get a new vector. Now we notice the following, that if you pick any vector in R2, any arbitrary vector, so you don't care what A and B are, it will always be possible to write that vector as a linear combination of u1 and u2, because this AB will be the same as A multiplied by 1, 0, which is u1, plus B multiplied by the vector 0, 1, which is u2. So any vector you pick in R2, it will always be possible to write it as a linear combination of these two vectors, u1 and u2. Yeah. So this is a definition of a linear combination. If you have a vector space V over R, and let V1, V2 up to Vn be vectors in R, it should be Rn, sorry. These should be vectors in Rn. So make sure you note this correction again. On the second line on page 21, this where the mouse is here, it should be R superscript n. So it should be R raised to n. That was left out. So we have vectors in Rn. Then we have scalars alpha 1, alpha 2. Okay. Now the thing is, the number of vectors should not be the same as the dimension of the space. So maybe we can put, instead of Rn, you can put something else. You can put M up here. Rm, M for Maragoli. So if you have any scalars, alpha 1, alpha 2, alpha n in R, then this vector obtained by adding the multiples of V1 up to Vn is what we call the linear combination of the n vectors. So we have n vectors, and they are all, oh, sorry, this should not be R, this should be V. They should be vectors in V. So you replace the R with V, because we know what the vector space, the symbol, the subset for the vector space is represented here by V. So replace this R by V. So that would be, let V be a vector space over R, and let V1 up to Vn be vectors in V. So replace this R with V. So V is any vector space. It can also be Rn as an example, but it works for any vector space. Like I said, we shall look at other vector spaces which are different from Rn later on. So you replace this R with a V. I hope you have noted down page 21.
What about, you said something like adding an n?
No, there's no, remove, forget about that.
So it
one.
just becomes the V alone.
Yes.
Okay.
Forget about the first correction I made. It's just V. So alpha 1 up to alpha n are scalars. And so this expression here is what we call the linear combination of the vectors alpha 1, vectors v1 up to vn. So what this simply means is that you multiply each vector by a scalar, and then you add them. Then what you end up with will be a linear combination of the vectors, as we did in the first example. Let's look at another example. Let's say v1 is equal to 1, 1, 0, v2 is equal to 1, 0, 1, and v3 is equal to 0, 1, 1. So this is a vector space R3. The vectors are from there. So we can get a linear combination of these three vectors, 2v1 plus 3v2 plus 4v3. And when we work it out, we get a new vector, 5, 6, 7. So we've been able to obtain a new vector just by getting a linear combination of the three vectors. So we've seen that 5, 6, 7 can be written as a linear combination of v1, v2, and v3. Now it is possible to show that any vector in R3 can actually be written as a linear combination of these three vectors, and we shall see how to do this later. So it's possible to show that any vector you pick here can be written as a linear combination of those three. So let's look at the next example. Here we have u1 and u2 as our two vectors in R2. So the first two are vectors from R2. Then the next one is v1 and v2. These are vectors from R3. The first question asks that we express the vector 7, 8 as a linear combination of the two vectors u1 and u2. The second one asks that we express the vector 0, 3, 1 as a linear combination of v1 and v2. So let's tackle the first one. To be able to express 7, 8 as a linear combination of the vectors u1 and u2, we need to find two numbers. We call them alpha 1 and alpha 2, such that 7, 8 is actually a linear combination of u1 and u2, so that 7, 8 will be equal to alpha 1 u1 plus alpha 2 u2. So we already know what u1 is, we already know what u2 is, we just make the substitution. And now we have this new setup, which says that alpha 1 plus alpha 2, 0 should be equal to 7, 8. Now you can set it up as a system of linear equations, so that alpha 1 plus alpha 2 will be equal to 7, and alpha 1 plus 0 is equal to 8. So clearly from here, alpha 1 must be equal to 8. And this forces alpha 2 to be -1, right? That would be the solution. The scalars we are looking for are that. So we can verify if what we got was correct. So we multiply the vector u1 by 8 and the vector u1 by -1. And when we evaluate that, we end up with the vector 7, 8, which is exactly what we wanted. So we've been able to express 7, 8 as a linear combination of these two vectors, 1, 1 and 1, 0. The coefficients we have obtained are 8 and -1. So the second example is now in R3, but the idea is the same. We want to express this vector 0, 3, 1 as a linear combination of the two vectors, 1, 2, 0, and 1, -1, 0. Just give me a minute. I need to respond to a call. Okay, so I was setting up a class for the one that starts in about 10 minutes. So if we check this setup, we do something similar to what we did in the first part. We look for scalars alpha 1 and alpha 2 such that 031 is equal to alpha 1 v1 plus alpha 2 v2, where v1 and v2 are as given. If we set up the system, we end up with a problem because the last equation here says 0 is equal to 1. So this means that it is not possible. We have tried to look for the scalars, but we end up with an impossible situation where 0 is equal to 1. So it is not possible to write this vector as a linear combination of v1 and v2. So that's the conclusion we come to, because when we try to do that, we end up with a contradiction. So 0 is not equal to 1. So here is a definition. So if let V be a vector space over R, and let V1, V2 up to VR be vectors in V. So we set the set S to be equal to contain just these vectors, V1 up to VR. So now the set of all the linear combinations of the vectors in S is called the span of S. So if the span of S simply means you get all the possible linear combinations of the vectors in S. So let's try some examples. I think that's the last thing we'll cover. So this example asks us to determine the span of the following sets of vectors. The first vector is U1, which is just 1, 2. The second set of vectors is U1 is 1, 0, and U2 is 1, 1. Again, that is still in R2. And the third one is 2 vectors. One of them is U, the other one is V. And they're both vectors in R3. So we'll start with the first one. We find the span, all the possible linear combinations of this one vector. So before we proceed, we shall work on some notation. So it says that S, if the set S is this V1 up to VR, the span of S will simply be denoted by span S. So basically, the span of S is a set of all linear combinations of the vectors V1 up to VR. So the scalars are picked from the real numbers. And if you keep changing the scalars, you keep getting more and more vectors in the span of S. So using that notation, we shall proceed. We want to find the span of this one vector, 1, 2. So it means we need to find all possible multiples of this one vector. And this will be all vectors of the form alpha to alpha. So this is basically the set of all vectors on the line y is equal to 2x, where the first coordinate, the second coordinate is equal to twice the first coordinate. So the span of this vector here is actually this line. All the vectors on this line, they make up the span of this set. So we observe that the span of 1, 2, of this vector 1, 2, cannot be the whole of R2. It's just made up of only the lines, the points on this line. Anything outside this line will not be in the span of this vector 1, 2. So let's look at the next example. So to find the span of U1 and U2, again, we need to find all the possible linear combinations of the two vectors. So we try to set up the linear combinations where we have alpha 1, 0 plus alpha 1, 1, 0 plus alpha 2, 1, 1, where alpha 1 and alpha 2 are real numbers. So when we add this up, we end up with alpha 1 plus alpha 2 and alpha 1, where alpha 1 and alpha 2 are real numbers. So this gives us the set of all possible linear combinations of these two vectors. So we realize that if you later on we'll see that this is true, but for now we can just observe that any vector in R2 can be written in this form: alpha 1 plus alpha 2 and alpha 1. We shall see this as follows. So basically what we are saying is that the span of these two vectors is the whole of R2. It's the whole plane. Any vector in the plane can be written as a linear combination of those two vectors, or can be written in this form: alpha 1 plus alpha 2 and alpha 1. Now to find the scalars for any vector, let's pick any vector in R2. Then observe that if you take alpha 1 to be A minus B and alpha 2 to be just B itself, then AB can be written as A minus B plus B, and then B at the bottom, because this is just 0. 0 plus B will give us B. And we still end up with AB. So we have shown that any vector, it doesn't matter what A and B is, it's always possible to write them as a linear combination of 1, 0 and 1, 1. So, but the scalars that you will need will be A minus B as your alpha 1 and B as your alpha 2. So as an example, if we take the vector 2, 3, we'll be able to write it as a linear combination of 1, 0, the vectors 1, 0 and 1, 1. We use these coefficients. Alpha 1 will be A minus B. So if A is 2 and B is 3, alpha 1 is 2 minus 3. And alpha 2 will just be B. So alpha 2 will be 3. So you can check that this is indeed 2, 3 is equal to minus 1 multiplied by 0, 1 plus 3 multiplied by 1, 1. And this is true for any other vector in R2. So again, here it means the span of these two vectors is the whole of R2. And any vector AB in R2 can be written as a linear combination of U1 and U2. And the coefficients would be A minus B and B. Okay. So we cover the last one now. This one says the span of, we have two vectors. in R3. That is 1, 1, 0 and 0, 1, 1. Now the span of these vectors will simply consist of all linear combinations of U and V. So this will be alpha 1 multiplied by 0, 1, 1 plus alpha 2 multiplied by 1, 1, 0. And when we add these up, we end up with the final vector is alpha 2 and alpha 1 plus alpha 2, alpha 1. So any vector of this form will be in the span of V and U. So if you want vectors in the span of V and U, we can simply, if you pick any pair of numbers, alpha 1 and alpha 2, as long as the second pair is the sum of the first and the third, then that vector will be in the span of V1 and V and U. Let's look at an example. So we can, if you want to construct a specific vector in the span of U and V, we simply fix the two scalars, alpha 1 and alpha 2, and we construct the vector of this form. So such a vector will definitely be in the span of the two. So we take a specific example where alpha 1 is 2 and alpha 2 is 3, and using this setup here, construct this vector. So this should be alpha 2 is 3, we put 3 up here. The second one is alpha 1 plus alpha 2, we add 2 plus 3, and the last one is alpha 1, and alpha 1 is 2 here. So this gives us 3, 5, 2. So this is an example of a vector which can be written as a linear combination of the two vectors U and V. And you can confirm that 2, 5, 2 should be equal to 2. Is it 2U plus 3V? Is that correct? Yeah, I think that will be correct. So we have confirmed that this vector is a linear combination of these two. And anytime you want to produce another vector in the span of the two vectors, you want such a vector, simply pick two numbers and construct a vector using this setup here. You will end up with a vector in the span. So what we'll also observe is that if any other vector in R2 cannot be written in this form, where the second slot here is the sum of the first and the third, then that vector will not be in the span. So for example, this vector 1, 3, 1 will not be in the span of U and V, because if I add 1 plus 1, I get 2, but here the second slot is 3. So the only way it can be in the span is if the second slot here is the sum of the first and the third. So that means there are some vectors in R3 which are not in the span of U and V. And this means that the span of U and V is not equal to the whole of R3. It is just a subset of R3. So we can describe the span of U and V as a plane which goes through the origin in R3 and contains the vectors U and V. And any other vector, say W, on the plane can be obtained by, you see, if this is W, I can obtain it by simply moving in the direction of U and then in the direction of V. But sometimes I have to move a direction that is beyond U. So to get that point at which I have to go, I'll multiply U by alpha to extend the vector U. The same might happen also for V. I may need to extend V. So I may have to multiply V by some scalar to extend it, so that W will be the linear combination of U and V. So basically this is a a plane in R3 which contains the two vectors u and v. And we have seen that, it must pass through the origin. So I think that's a good place to stop, because I have to go for another class from now until 2 o'clock. Are there any questions? So are there any questions? So I hope you will all be able to check SOMAS. I recorded the class, so I will share it almost immediately or as soon as possible. But the other thing also is these notes are available on the SOMAS platform. There's a link that you can click on. I think it's under resources. You can double check that. There's a link you can click on to obtain this set of notes. You can download and read on your own, and also try to watch the video. I will send the link to the channel. I'll set up a YouTube channel where I can put these classes, and I will send the link to the class. Then you'll be able to join to watch on YouTube. So have a great evening or afternoon.
Thank you. Thank you.
Okay. But you need to have some questions. I hope next class you will have some questions.
Yes.
Okay.
Yes, sir.
Silas, you will have questions.
Yeah.
Good. Okay, so I will leave so that I can start the other class now.